So, welcome back. Hopefully, everybody out there is staying safe, staying healthy, uh, doing pretty well. If you haven't yet watched the videos from today's videos are day 33. One thing you will find is that there is a special guest in the video, so I encourage you to do that. The guest was very, very pleased with herself for her taking over, frankly. And otherwise, the videos today were really discussing the first part of it discussed how we implement sorting. In how the sorts are actually implemented. They go through the two sorts that are used in the Python sort function, selection sort and merge sort. And then the bigger thing is it goes through searching. So what I have today, there isn't a lot of code, frankly, from this lecture. This lecture was mostly to sort of present ideas that will be coming up and that you will need in future classes, 116, 191, 250 being chief among them. But what I did want to do is just go through the linear search process and binary search process a little bit. Again, all of the code from the lectures today, the videos today that we're going to go over here, we're not expecting you to memorize it. Please don't. We're not expecting you to be able to create it just immediately on your own. Again, not a very useful skill. But the bigger picture, the bigger ideas, that's sort of what we're looking for. Do you understand how things are working? So we'll go into it in a few seconds. One other thing, I don't know if you all get these mails from, well, many of you probably still live with your parents. When you're in school, maybe you get these mails from your parents. I get these mails from my parents still. The mail my father sent to me today, actually sent to my entire family today, was talking about different skills that you should have while you're on lockdown, while we're all in stay-at-home orders. And one of the suggestions was that you should dress for the social life you want. For the lab exam this week, do we need to know about bottle.run? Well, it's valuable to know, yes. Am I expecting you to memorize it? Well, apparently you did. It's bottle.run, and then, was it 0. Path equals 0.0? I don't remember. So the answer is, do we expect you to memorize it? No. How do you know? I don't memorize it. I don't have it memorized. I have to more or less look it up each time. So hopefully that answers that. At any rate, the mail that I got from my father said that you should dress for the social life that you want rather than the social life that you have. So I don't know about all of you, but currently I'm in my Batman onesie because if I were able to have a social life right now, I'd love to be going around dressed as Batman. That sounds like kind of fun. Something that we all need. So hopefully you can be equally comfortable. Anyway, now that I've shared that little bit of the story and honestly just given people time to check in, what I did want to go over today is how we do searching, and not so much that searching itself is that important. It's kind of fairly straightforward. We don't expect you to have this code memorized, but just to talk about how we measure searching. That's, again, something that'll come up in the future, and how we can use this for debugging code, for checking code, for doing the sorts of things that you are going to still need to do throughout the remaining, actually, there's only 3 weeks left of this semester and in future times. So for the first example here, what I have is a simple linear search function. So what we're going to do is we're going to take in a list. We're going to have a target. That's what we're searching for. And we want to return true if that item is in the list and false otherwise. Hopefully straightforward. So what I did was I created a it's called a local variable, just a variable. I named it compares. That will just keep track of how many comparisons we do. And that's just so I have an idea of what's going on, how much work we've done. It's a good way when we're talking about searching or actually sorting, how we can compare things. And it's actually a good way to debug. It's useful to see what's been going on because that can often tell us where any errors are. So I initialize that compares to 0. Then I say for each entry in our list. Now what I'm about to do is a comparison. So I increase the value of comparison by 1, compares by 1. And then I say, if the entry is equivalent to the target, then I will print out, I have ls here just to say linear search so we can see it. The target was found after however many compares it took. And I return true. And when that's not the case, and because honestly, this is a very common mistake I see students doing, I have an else, and again, we'll just output not found and the number of compares and return false. So I have here just a list of initials. Honestly, I don't know where I came up with these. These are just honestly a couple of strings that I'm looking for. The data that we could be searching for is anything, right? We're not really using the data in any way. We're just searching for it. So it seemed reasonable. And then I have a bunch of different searches. So I have a search for LP, which you'll note is in the list at the very end. Well, we can start with that one. Let's just do that. So if I run this, what you'll see is that it returns false, which is obviously not correct. LP is in the list. And so that might be confusing. That might be weird. That might be hard to fix. But note that it says there's been one, and then I didn't do it properly. So it says one compares rather than one comparison or something like that. And, the reason why that happens, of course, is if we walk through this code, what do we see? Well, we set compares to 0. Go for entry in list. So we'll start with the entry at index 0. So that's AR. So entry is AR. We increase the value of compares to 1. We then say, is AR equal to LP? And of course, the answer is no, it's not. That guard expression is false. So we immediately go to that else, and we're done. That's not very helpful. This sort of, by walking through the code, we can see that this else isn't appropriate. And this is sort of one of the lessons from the lecture. One thing to think about as you are doing bigger and bigger pieces of code. First of all, every if doesn't need to have an else. More importantly, usually we only want to do a return value when we know the answer. So this return true, that makes sense, right? As soon as we find a match, the answer has to be true. We should stop wherever we are. We don't need to continue it on. We could, but it's kind of silly. On the other hand, this false, we don't know, right? Just after this first comparison, we have no idea if that's going to be in there. So we can't include this return false in the results. If instead we wait till we get done with that loop, well, what does it mean if we're done with this loop? Let me get rid of this else. Well, one thing I'll add, actually, I could write it like this. This is a very unusual aspect of Python. If you see I ran it, of course, LP does exist, so let's give it LX, which does not. Python, and as far as I know, Python is the only language like this, actually allows you to have an else after a for loop. So this else is actually attached to the for loop, not to the if. And it just is executed whenever we get out of this loop. I wanted to show this to you to let you know that it does exist, that it is possible, and also to tell you, please never, ever, 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 ever use an else on a for. it is a good way to, frankly, make lots of mistakes because you're going to assume it's associated with an if statement and it just doesn't work. So we can get rid of that, and it works just as well, right? If I look for LX, it's going to say I can't find it. If I look for LP, of course, it says it does, just like you would expect. And the reason this works is, of course, inside this loop, we're going to go through each entry, and if there's a match, we're going to return true. Remember that a return statement ends a function call immediately. Do not pass go, do not collect $200, right? Everything is over immediately. So the only way we can get out of this loop is if we went through each entry and list and never found a match. Well, if we've been through each entry and list and we never found a match, then the result is false. We're good. We don't have to go further. So, I can do this for a number of different things. So we can search for JL, which doesn't exist. It's actually too far beyond there. FW, which is here in the middle. AR, the first thing. AA, it's even before that. And if I run all of these, what you're going to see is that when it's not found, whether it's too early or too late, it's going to take 9 comparisons. On the other hand, when it is found, it takes a variable number of comparisons. It might be as simple as 1, if we're looking for the first thing. It could be as many as 8, which is how many things there are in here if it's the last one. So this is kind of the big downside of linear search. If we're searching for data early on, one of the first values, then it actually is pretty fast. But if we're not going to find something, or if what we're looking for is at the end, then it's going to be honestly really slow. Now, there is a way we can improve this, right? So as it happens, hold on a second. I was going to say this is in alphabetical order, but it's not because LMNOP, Q, R, S. Yes, Q comes before S. So now, if I remember correctly, if I can do this correctly, it is in alphabetical order. Wait, H, I, J, K, L. No, it's not. Let's switch this around. One more. If we have it in alphabetical order, now we have it in alphabetical order, then we could try to speed this up a little bit. So I'm going to change this over to, actually, I'm going to just make a new function. I'll make a function ordered linear search. Change our calls to use that. Right, and now what do we know? We know it's ordered. Why it not returning the Boolean? So I'm not sure what you're referring to for it, but every function in here is returning a Boolean. So, right, we have return true or return false, and now for ordered linear search, we have return true or false. If you're saying, why do you not see a Boolean here on the console? Remember that a return statement is just to the program, right? Return is how the computer communicates with itself. So it does return something in each one of those calls, but I don't print it out. To see it on the console, we have to have a print statement. So does that answer your question? Hopefully. Okay, good. So if we have an ordered linear search, then we can speed this up a little bit, right? So for instance, if we're looking for AA and we get to AR, well, AR occurs after AA. There's no way that we're going to find it. So in that situation, we actually can include something in here, right? There's a way that we can cut it off early in order to understand what's going on. Now, what we need here is we can't do else, right? If we do else, and do the same thing, then it gives me an error for reasons I can't figure out right now. Oh, because I didn't indent it properly. There we go. Then you can see it's not working again, right? Just saying else, well, of course, that all that does is that says, well, do we have a match on that first thing? So we can't do an else, but we can do an elif, right? What we can do is say, well, let's think about it. If the entry, so when we have AR and we're searching for AA, well, AR is too big, right? So if the entry is greater than target, that means that we're too big and we can stop immediately. And so if we actually run this now, what you see is it still works, but those worst cases can still be pretty bad. Suppose rather than LP here, I have LX, that's afterward. Right, note that we could take up to 9 comparisons, and in fact, actually, it would be more than that because we might have 2 comparisons here, in order to be able to find things. So yes, this speeds it up a little bit when we are searching for like AA or JL, where it can dump a little bit early, but not really all that much. And in fact, when we tend to think of processes like this, we tend to think in terms of the worst case. So there are some algorithms out there that are very, very fast in general, but they have a worst case that's, something on the order of like taking years to complete. Well, it could be that you're pretty quick normally, but every now and then it takes a year or two to complete. That's not actually helpful to anybody. And so we don't use those. So this does make it a little bit faster, but not much. In comparison to that, we're going to talk about binary search. So let me actually comment all this out real quick, just so we know what we're looking at. So binary search is going to be a lot faster. So I'm going to do the same sort of approach, right? I'm going to keep track of how many comparisons we have. And just so you all can see how this works, what I'm going to do is I'm going to print out our work as we go. So what binary search is going to do is it's going to keep track of 2 variables, left and right. And we're going to slowly, I can't do alphabetizing here either. We're going to very slowly, it needs the data to be in order, which means I probably should put it in order. There we go. What it's going to try to do is it's going to slowly sort of center in on where it's going. So left, this variable left, that's going to be the leftmost index where the data can occur. Right is going to be the first location, the first index where the data can't occur. So right is actually beyond the edge of the data that we're considering. So in the beginning, we'll say, well, it could be anywhere from 0 to the end of the list. So 0 is the first location it can occur. We'll set that to left. And for right, the length of the list, right, that's 1 after the last index. That's the first location it can't occur. So we'll set that to right. And then we'll keep track of the number of comparisons. And what I'm going to do, just so that we can see what's going on, I'm going to have every time we go through this loop, I'm going to print out to the value of left and the value of right minus 1. So what range are we considering? And then what we're going to do is we're going to look at the midpoint between those two. So here's our range. We're going to look at whatever is the index in the middle, more or less. If it's an odd number, we'll just round down. Doesn't really matter. And we'll compare the value at that location with our target. If our target is smaller than that value, well, in that case, we know that if it's smaller, what did we do? We went 2 locations, and I actually forgot to do this real quick. If it's smaller, well, what that means is that everything that's larger than that midpoint is too large. We only have to check everything that's smaller. If our target is larger than that midpoint, that means everything that's smaller than that midpoint, everything to the left of that midpoint is not valid. We can just get rid of those. Obviously, if it's equal, we found it. And so we're going to keep this loop up. But what we're going to do is two things. One, at the end, we'll say, here's our new solution range. But note that this will slowly center in on where that location is, hopefully. But we still may not have a match. And so how do we know we don't have a match? Well, if the range that we're considering doesn't exist anymore. So if that rightmost value is suddenly equal to left, remember we don't consider the right index, or less than that, that means we don't have a range to search for. The item doesn't exist. So in that case, we say not found. And so just to show you how this works, suppose that we're looking for LP. So if you remember before we had to go through the entire list in order to find it. Now it's going to be a little different, right? At the beginning, so this first printout, we're going to say, well, we're looking from 0 to 8, anywhere in there. What we're going to do is we're going to compare that midpoint. So it'd be index 4, 1, 0, 1, 2, 3, 4. So we'll compare LP and FW. LP is greater than FW. So what we're going to do now is we're going to say, okay, our range is now just indices 5 through 8, right? By doing that comparison, finding out that we're greater than FW, we can not only eliminate that one, but we can eliminate all of these. And so now we're going to continue just with 5 to 8. We'll again find the midpoint, and the midpoint is going to be 5 plus 8, which is, I hate math. 5 plus 8 is 13. 13 divided by 2 is, 13 divided by 2 would be 6.5. So 6, roughly. It's going to have to be 7. So, oh, right, because it's 5 plus 9. Math is hard. We're going to look at, I probably should add the midpoint to this. Do that. Hold on a second. I'm going to add something because I'm trying to debug this. And here's a neat trick for all of you. Don't do things in your head. Just print it out. It's so much easier. So now we can see where the midpoints are, where the value of mid is, right? So we have this range 5 to 8. We said our midpoint is 7. So 7 is this JK. We compare LP and JK. Of course, LP is larger. So what we're going to do is we're going to again look at that largest value. We're going to just increase and say, okay, everything in JK and below JK now is eliminated. So our range is from 8 to 8. So what we're saying is if that LP exists, it can only exist at that one index. And when we do the index, we return that that's actually correct. So note that we didn't have to do nearly as many passes. We didn't have to check out each one of those values in order to see that we have a match. If we don't have a match, so here I'm going to look at JL, then we're going to do the same basic process, right? We're going to go from 0 to 8. It's too large. We could compare at index 7, which is JK. And of course, it's larger than JK. So now we have 8 to 8. We check that LP. It is smaller than LP, so we can eliminate everything here and up. And so then our value of right is going, or our value of left is going to be 8 still, right? We're saying that this is the smallest index where it can occur, but our value of right is 7. We're saying it has to be at that index or earlier. Well, there's no value that matches, right? There's nothing that's in between these two and actually that is less than that and greater than that. That can't exist. So in that case, we know we didn't find it, and note it takes fewer comparisons. So again, even if we're searching for something at the end, it goes a lot quicker. So, we can, if we're searching for something actually in the middle, so here I'm going to search for FW. This actually is a weird case. It finds FW immediately. It happens to be, coincidentally, almost as if I planned this out, that FW is the midpoint of that range. And so rather than, again, searching through everything because it starts at that midpoint, the best case for binary search is when we have something at the midpoint. Where binary search actually does worse than linear search, and I'll just print these two out together, is when we're looking for something at the very beginning. And the reason why is that we're constantly going 1/2, right? Each time through this range, we're shrinking what the range can be by 1/2. And so in order to find that first thing, it's going to end up taking 5 comparisons. If it's not found, it actually does it a little bit faster, but still not particularly great. It takes 4 comparisons. The point of this being that, yes, this is our worst case, but this is actually a lot faster than that linear search. Here, our worst case is, and don't worry about how I come up with this, because honestly, I can't explain it. I just know the facts. I just know the computer science, would be log of n. So log of whatever our size of our array is. So yes, this can be a little bit slower, but it's not as common, and its worst case isn't as bad. So whenever we implement this, we always implement, whenever we do searching, we always do some form of binary searching. You're going to see this pattern. It's called divide and conquer. This pattern a lot as you go on into future classes like 191 and 116. So do these ideas make sense to everybody? How I went about debugging it, just seeing what's going on, tracing out what's going on, following it line by line, because that's how the computer has to execute it, in order to find any bugs. Okay, seems like people are okay. Does anybody have any other questions? Anything else that they want me to go over? Since that's pretty much the material from today's lecture. Could be a question about something else if needs for code. Okay, I don't see any questions, which is fine. We're going to be getting back into a little bit more hard code coding on Monday. On Monday, and all next week, we're going to actually talk about databases. So another way that we can have stored data in our program. This is going to be persistent storage. That is storage that lasts beyond the single running of a program. So a different way of doing it. We've talked about text files and CSV files. Databases is a different way of doing it that's much more optimized towards storing and searching for data. So we'll be talking about that next week. Other than that, thank you all very much. If you have more questions, I do have office hours at 4. I know TAs have office hours on Zoom all the time. My office hours are on WebEx. Otherwise, thank you all very much. Remember that there is the project part 3 due this evening. The final project, the one that's actually worth the vast majority of the points, is due in, I think, like 2 weeks from now. So you have a little bit more time for that. And with that, thank you all and have a good weekend. Stay safe, stay healthy, and try to have a little fun. Thank you.